Here's a function, pi raised to the x. In the real number world, this exponential behaves perfectly. Its derivative follows the standard rule. The derivative is pi to the x multiplied by the natural log of pi. But everything changes when a negative sign is introduced, negative pi raised to the x. Suddenly, the usual rules seem to break, because most graphing calculators refuse to plot it. A message appears, calculation error, leaving a blank space where a smooth curve is expected. And yet something still exists. At whole number x values, real outputs appear. 1, negative 3.14, 9.8, and negative 31. Here, negative pi raised to x doesn't form a normal real curve. Only the integer x values show real outputs. The dashed path is just a guess. The real behavior is hiding in the complex plane. So what curve connects those dots? And if this function is a glitch, what does its derivative even mean? Negative pi to the x looks broken on a real graph, but it's not random. The key is to rewrite it using exponentials. Negative pi to the x can be written as e to the power of x times the natural log of negative pi. Now the natural log of a negative number is multi-valued. In general, the natural log of negative pi equals ln pi plus I times open parenthesis pi plus 2 pi times k close parenthesis, where k is any integer. So there are actually infinitely many possible complex versions of this function, one for each k. But to get a single consistent curve, a branch must be chosen. On the principal branch, k is 0, so the function becomes e to the power of x times open parenthesis natural log of pi plus I pi close parenthesis. That means it grows in size while also rotating. And that's why the curve turns into a spiral, not a real curve at all, but a complex motion hiding behind the glitch. Now the derivative can be computed cleanly. Start by rewriting the function. Negative pi to the x equals e to the power of x times the natural log of negative pi. Now apply the chain rule. So the derivative becomes natural log of negative pi times e to the power of x times the natural log of negative pi. But the key question is, what is the natural log of negative pi? On the principal branch, negative pi has magnitude pi and angle pi radians. So natural log of negative pi equals natural log of pi plus I pi. Now substitute that back in. The final result is the derivative of negative pi to the x equals open parenthesis, natural log of pi plus I pi close parenthesis, times negative pi to the x. So the glitch wasn't a failure, it was a complex derivative hiding in plain sight. Now the derivative can be seen as an action. In the complex plane, f prime of x isn't just a formula, it's a transformation. Start with the original function, negative pi raised to x. As x increases, it traces this blue spiral outward. Now plot the derivative and a second spiral appears. It looks related, but it's wider and it's turned. Mathematically, the derivative equals the original function multiplied by a constant, the natural log of negative pi. To see this clearly, look at x equals 0. The function value is 1, so the vector points straight to 1 on the real axis. To get the derivative vector, take that original vector and apply the constant. First scale it by the size of the complex log, about 3.34, then rotate it by the angle of that complex log, a bit over 70 degrees. That new vector is the derivative. It represents the instantaneous velocity of the spiral, how the function is moving through the complex plane at that point. So in complex calculus, a derivative doesn't just describe a slope, it describes a local stretching and twisting of space itself. Thanks for watching.